So 1.6 continuity. Okay, so what is continuity? So when thinking about continuity, we consider when we're able to draw a graph without lifting our pencil. So in other words, there's no breaks or jumps in the graph. When we state a function is continuous at point P, we mean that the function passes through point P without a break. Okay, so passes through that point. In order to be continuous, the following must be met. So when I read this, it's going to be very similar to if the limit exists. There's just one additional part here. Okay, so the limit as x approaches a from the negative side of f at x, so the left side, I'm going to skip this, equals the limit as x approaches a from the positive side of f at x. Okay, so in other words, the limit must exist because these two conditions are the two conditions for a limit. There's one additional condition for continuity. These same two numbers must equal f at a. So it must equal that point, like that point must be filled in. In other words, there can't be a hole there. Okay, if these three requirements are not met, f at x is discontinuous at x equals a. Okay, and when we talk about discontinuity, so a graph is discontinuous if it has any break. So in other words, you cannot draw the entire graph without lifting your pencil. So let's consider the following graphs. Okay, so if we have a graph here, this is a closed circle, and this one zigzags up and down, and then closed circle. This is continuous for all values in the domain. Domain being like -3 to probably 7 here. Okay, so we've seen B before when we have a rational function and we factor out a binomial and we cancel it out, it becomes a hole, right? A lot of times we're left with a linear function, but with a hole in there. So in other words, if we're drawing this line, oh, we get to a hole. You have to pick up your pencil, relocate on the other side, and then keep going. So when there's a hole, we say it's discontinuous at 1. And this is called point discontinuity. Okay, and we're always looking at the y's, quoting in the x's. Okay, there's also something called jump discontinuity. So, for example, and remember, we read graphs from left to right, and that's why I'm starting on the left-hand side with all of these graphs. So the very most left point is here. We come all the way to almost 4, but not quite to 4 because there's an open circle. We have to pick up our pencil, relocate, and then continue our graph. So because there's a huge gap there, there's a discontinuity at, again, 1. Okay, and again, this is called jump discontinuity. And then we've seen this before with rational functions, especially in advanced functions. Okay, we can also have infinite discontinuity, and that's when there's a vertical asymptote. So if there was a vertical asymptote at x equals 1, what this would look like is going all the way over to the left and starting from the left and drawing this to the right. So this would be continuous if it was only this part, but unfortunately we have to pick up our pencil, go across the vertical asymptote, and start going to the right again. So infinite discontinuity. So example 1, we're given a piecewise function. So A asks us, graph the following function. So f at x, so this is one function. We're going to consider both of these parts of the function at once. So we have x squared minus 3 if x is less than or equal to -1. So I'm going to show you a very hands-on way of doing this. So let's just focus on this part of the function, okay? So let's map out our domain. X is less than or equal to -1. So let's go every two boxes. -1, -2, -3, -4. And this is going to be 1, 2, 3, 4. Obviously 0 in the middle. And then this is going to be 1, 2, 3, 4. And it's going to be -1, -2, -3, -4. Okay, so we are going to consider this function when x is less than or equal to -1. So this is our point here. And we're going to consider this function on this side. Okay, I'm going to clear this. I just want you guys to have a visual, but I'm going to clear this so it's nice and neat. Now, what I do every single time is I sub in this -1 into this function. So f at x equals -1 squared minus 3. We get 1 minus 3, which is -2. Oh, this is f at -1. So we get the point -1 comma -2. When we locate this point, because we have the underline here, we can go ahead and fill in that point. Oh, I did that at 3. I meant at 2. Okay. Now, other than what's going on, because this is what essentially happens in these questions. When we're determining, say, for example, the limit as x approaches -1, what ends up happening is these numbers here to determine the limit end up being possible discontinuities, right? We have a possible discontinuity because we have two different graphs meeting up at one, like at a single point, like meeting up at -1, and we want to see if they actually meet or if there's a jump there. That's essentially what we're doing, okay? So see how this is x squared minus 3? We no longer have to get proper coordinates for this, so I'm just going to say for x squared minus 3, this is a parabola. The leading coefficient is 1, right? So it opens up. And I'm satisfied with this point. We can also say the vertex is 0, -3. So I'm just going to draw this like a sketch, okay? And this is going to go up to the left. Okay, so now let's take a look at the second part of the piecewise function. We have x minus 1, and this is for all x's greater than -1. So again, we have -1 right here, and we're looking at this section. We're looking when x is greater. So all of these numbers here and up to infinity. Okay, so let me clean that up. And what I would do, even though there's no underline, what I would do still is sub in this -1 into this function. The reason why I would do this is because we know that we're going to actually start at like -0.99999 forever. Because we're starting just on the other side of -1. So what we'll be able to do is substitute this -1 in, find the point, and then use an open circle for that point. So let's go ahead and put f at -1 equals, so it's -1 minus 1, which I get -2. So my point is -1, -2. I'm going to go ahead and plot that with an open circle. So taking a look at this graph, even though I've plotted it with an open circle, that circle is actually still filled in, but with the parabola formula. Okay, and with x minus 1, we have a slope of 1, like 1 over 1, and then we have a y-intercept of -1. So y-intercept is -1. we're going to go through that point. Then we can go up 1 over 1, up 1 over 1, up 1 over 1. Okay, so this is part of f at x. This is the x minus 1 portion of it. And this is also part of f at x. This is the x squared minus 3 portion of it. Okay, so we went ahead and graphed it. Now, determine the limit as x approaches -1. So what we have to do for this is we have to determine the limit as x approaches -1 from the left, okay, of f at x. And we have to ensure that the limit as x approaches -1 from the right of f at x is the same. So as we go into -1, we approach -2 from the left. As we approach -1 from the right, we also go to -2. So the limit is -2. And you can leave it like this. Okay? Now, C asks, determine f at -1. So in this case, we already subbed -1 into both sections of this function, like both parts of this function, just to estimate the graph. However, because this first section, which is f at x equals x squared minus 3, because this has -1 in the domain, because of that underline, right, that underline there, we're actually going to take f at -1 of this function. And we've already done this, it's -2. So -1 comma -2 is our answer. This is important though, because sometimes we'll get functions with 2 or 3 different parts of the piecewise function, and sometimes there is going to be a jump. So these two actually quote unquote meet at -1 comma -2, but sometimes they have a jump. So it's very important to consider which circle is going to be closed and which circle is going to be open. Okay, and D, is f continuous at x equals -1 and explain. So I'm going to do this as like a continuation of the limit. So we've already determined that the limit as x approaches -1 from the left of f at x equals, I'm leaving this blank, the limit as x approaches -1 from the right of f at x. And these both equal f at -1. So all of these are going to equal -2. The limit approaches -2, f at -1 is -2, I should say, and the limit as we approach -1 from the right is -2. So therefore, f at x is continuous. Example 2, test the continuity of each of the following functions at x equals 2. If a function is not continuous at x equals 2, give a reason why it is not continuous. Okay, so taking a look at A, f at x equals x cubed minus x. Well, taking a look at this, I think back to what an x cubed function looks like with coefficient 1. It's going to look something like this, where it zigzags up and down 3 times. So 1, 2, 3. Okay, at most it's going to have 3 zeros, and it's going to extend from quadrant 3 to quadrant 1. Now, we know that all polynomials are going to be continuous because you don't have to pick up your pencil. Okay, there's no vertical asymptotes, there's no horizontal asymptotes. So all polynomials are continuous. And if you think about the domain and range for these, like just logically, XER and XER. There's absolutely no restrictions on a polynomial. It goes in all directions forever. Okay, so they're continuous. Now B, we have g at x equals x squared minus x minus 2 all over x minus 2. So right now in the denominator, I look at this like there could be a vertical asymptote, but you always want to check for holes first. So for the numerator, because it's a trinomial, we can think of what two numbers multiply to -2 and add to -1. Well, I get -2 and 1. Okay, so I get x minus 2, x plus 1, okay, over x minus 2. At this point, we can cancel out the x minus 2's, and we have the line x plus 1 such that x cannot equal 2. There is going to be a hole because we canceled the numerator and the denominator. Okay, so we can say discontinuous at x equals 2. And then the reason why is there's a hole. Because there is a hole. So taking a look at C and B are very similar, whereas we have the same function here, h at x equals x squared minus x minus 2 all over x minus 2. And this time they do give us a restriction. They give us that restriction in the denominator. So x can't equal 2, of course, because we can't have a number over 0. Okay, cannot have 0 in the denominator. Okay, so if we do the same thing as above, we would factor it to x minus 2, x plus 1. We would put it over x minus 2, cancel those out. Now we have a linear function, x plus 1. But we know that that linear function is going to have a hole. By the way, when I see this, I think slope is 1. And y-intercept is also 1. So I'm thinking it looks approximately like this, except for there's going to be a hole at x equals 2. So just get rid of that inside, okay? There's a hole. Now, there's a little bit more to this equation. They're also giving us a little bit more information. They now say that there is an additional point to this function. So it's almost like a piecewise function because they're giving us a little bit more. They say h at 2 equals 3. So what I want to do is I want to find out where this hole actually is. So what we do is we take this 2 and we sub it into our h at x, which is our line. So I'm going to bring it over here. H at 2 equals 2 plus 1, which is 3. So this hole occurs at 3. Now, taking a look at this additional piece of information, they're telling us h at 2 equals 3. They're giving us the point 2, 3. Let's do this in red. They're giving us the point 2, 3 to actually fill in. So by us filling in 2, 3, this line now becomes continuous. So we're going to say continuous. Okay, we see that going into 2, we're approaching 3. Going into 2 from the right-hand side, we're approaching 3. And then we filled in that gap with h at 2 equals 3. Okay, those 3 components. Okay, D, f at x equals 1 over x minus 2 squared. Okay, so even if we were to expand this and we were to say, okay, x minus 2, nothing's really happening here. Nothing's getting canceled out. We're going to just directly have a restriction in the denominator. When we have a binomial in the denominator, we know that the denominator cannot equal 0. So x minus 2 squared cannot equal 0. Okay, since this is squared, we're going to square root both sides. X minus 2 cannot equal 0. And then we're going to bring over the negative 2. X cannot equal 2. Okay, that's how you formally state the restriction in the denominator. In other words, this is going to be discontinuous because there's a vertical asymptote at x equals 2. Okay, so to recap, if the binomial is only in the denominator, it's a vertical asymptote. If it's getting canceled in the numerator and the denominator, like we saw before in B and C, that is a whole. Okay, E. So let's take a look algebraically at a piecewise function. So this time I'm not going to be, I'll talk about it, but I'm not going to be graphing this. So g at x equals 4 minus x squared as when x is less than 2. And then 3 if x is greater than or equal to 2. Oh, I'm so tempted to graph this. So what we have to do is we have to take a look for continuity. We're going to take a look at like when the limit of g at x as x approaches 2 from the left equals, it's not f, it's g at a, so g at 2. And that has to equal the limit as x approaches 2 from the right, okay, of g at x. So we have to consider these three. So the easiest one to do is g at 2. Let's sub this directly in. So if we are trying to look for g at 2, which one of the parts of this function include 2? Well, it's going to be this underlying one, when x is greater than or equal to 2. So that's 3. So we have the point 2, 3 here. So this point in the middle is 3. Now what we have to do is we have to consider this graph from the left and this graph from the right, and we have to think, does it approach the same number? Does it approach 3? Okay, well, logically, this is a horizontal line at 3. I'm giving in. I'm caving. So this is 2. This is going to be 3. So this is going to be filled in, and then it's going to be a horizontal line for every single number above 2, right? So we do get 3 for this. And then if you think about 4 minus x squared, this is when we take this value 2 and we sub it into here. Even though we may have an open circle and we may have a discontinuity, we still know that this is a parabola, right? We see an x squared, and it's a parabola that opens downward. But because a parabola is a polynomial and a polynomial is continuous, we just need to know kind of like the starting point or the point at 2. So let's go g at 2 equals 4 minus 2 squared. So I get 4 minus 4, which is 0. So this parabola goes through the point 2, 0. So if we were to put that on our graph, we would get our open hole here. And this graph, if you think about x squared, negative x squared plus 4. I believe it opens like that. So what I would put here is because it approaches, this approaches 0 from the left. So 0 does not equal 3. So I'm going to say that this is not continuous. Therefore, discontinuous at x equals 2 because of a jump. There's going to be a jump in that graph. Okay, and algebraically, even if you didn't draw the graph, you can see that when we plug in 2 to the parabola and 2 to the line, we're getting different numbers. Okay, that means they're not meeting up.